In this session, we are going to study about transverse vibration of a stretched string. Consider a string of length AB. Let M be the linear mass density of the string and T the tension in the string. Let the equilibrium position of the string coincide with the x-axis. Now when the string is plucked up and released, it vibrates vertically. Now consider an elementary section of the string of length delta x, which is lying at a distance of x and x plus delta x from the fixed end. Let T1 be the tension acting on the elementary section of the string and T2 be the tension acting on the elementary section of the string. T1 makes an angle alpha with the horizontal and T2 make an angle beta with the horizontal. On resolving T1 and T2, we get T1 sin alpha and T1 cos alpha as the components of T1. The components of T2 are T2 cos beta and T2 sin beta. Now we can equate the horizontal force and vertical force acting on the elementary section of the string. Now first we can take the horizontal force acting on the elementary section and equate to the form F equal to ma. Now the horizontal force acting on the elementary section of the string is T1 cos alpha and T2 cos beta. Now all force towards my right I am going to take it as positive, and all force towards my left I am going to take it as negative. So difference in horizontal force is T1 cos alpha minus T2 cos beta is equal to 0, because when the string is plucked up and released, it vibrates vertically. No horizontal motion, therefore acceleration along the horizontal direction is equal to 0, or T1 cos alpha is equal to T2 cos beta. Now we can equate the vertical force to the format F equal to ma. The vertical forces are T1 sin alpha and T2 sin beta. Difference in vertical forces T1 sin alpha minus T2 sin beta is equal to mdl into d squared y by dt square. Mdl represent the mass of the elementary section. Now we know T1 cos alpha is equal to T2 cos beta, or T2 is equal to T1 into cos alpha divided by cos beta. When you substitute for T2, we get T1 sin alpha minus T1 cos alpha by cos beta into sin beta is equal to mdl d squared y by dt square. Taking the common term out, we get T1 cos alpha into sin alpha divided by cos alpha minus sin beta divided by cos beta equal to mdl d squared y divided by dt square. Now we know the horizontal forces are balanced, that is T1 cos alpha equal to T2 cos beta. Let it be equal to T. And we know sin by cos is tan. Therefore, the above expression can be written as T into tan alpha minus tan beta is equal to mdl d squared y by dt square. Now tan alpha is nothing but slope at x plus delta x, and tan beta is slope at x. Therefore, the above equation takes the form T into slope at x plus delta x minus slope at x is equal to mdl d squared y by dt square. Simplifying, we get T into slope at x plus delta x minus slope at x divided by delta x. Delta x is same as dl is equal to m into d squared y by dt square. Difference in slope of 2 points divided by the separating distance is second derivative, and our wave function depends on more than 2 variables. So changing the total derivative to the partial derivative, we get t into difference in slope divided by separating distance is equal to m into d squared y by dt square. So we can rewrite this expression as t into dou squared y by dou x square is equal to m into dou squared y by dou t square, or dou squared y by dou t square is equal to t by m dou squared y by dou x square comparing it with one-dimensional wave equation, that is dou square psi by dou t square is equal to v square into dou square psi by dou x square, we get velocity is equal to root of t by m. That is, the velocity of the transverse wave is equal to root of t by m, where t is the tension and m is linear mass density of the string. Now we can derive the expression for frequency of transverse vibration of a stretched string. Before that, we should know what is a standing wave. A standing wave is a pattern that is created when two waves having same amplitude, same frequency, traveling in the opposite direction interfere with each other. When standing wave is formed, there will be node and antinode. Node is a position of minimum displacement and antinode is a position of maximum displacement. And node distance of a wave is lambda by 2 and node antinode distance is lambda by 4. So when the string is set into transverse vibration, the forward moving wave will get reflected from the fixed end. Therefore we have two waves having same amplitude, same frequency, traveling in the opposite direction. They will be interfering with each other to produce standing wave pattern with one segment, two segment, and so on. Now if it is vibrating with one segment, then the relation between length and wavelength is L is equal to lambda by 2. We know velocity v equal to f lambda, f is equal to v by lambda, and the expression for velocity of transverse vibration of a set string v equal to root of t by m, and if it is vibrating with one segment, lambda equal to 2L. Therefore the expression for frequency is 1 by 2L root of t by m. If it is vibrating with two segments, then the relation between length and wavelength is L is equal to lambda. Velocity is equal to f lambda, f equal to v by lambda, and the velocity we know it is root of t by m, lambda equal to L. If it is vibrating with two segments, then f is equal to 1 by L root of t by m. It can also be expressed as f is equal to 2 by 2L root of t by m. If it is vibrating with two segments, expression for frequency is 2 by 2L root of t by m. If it is vibrating with three segments, then the relation between length and wavelength is L is equal to 3 lambda by 2. Therefore we can write the expression for frequency as f is equal to 3 by 2L root of t by m. We can generalize if the standing wave segment or the number of segments in the standing wave, if it is n, then the frequency of transverse vibration of a stretched string is f is equal to n by 2L root of t by m. So the expression for frequency of transverse vibration of a stretched string is given by f is equal to n by 2L root of t by m, where n is the number of segment, t is the tension, m is the linear mass density, and L is the length of the string. Now in the case of a guitar, 6 strings are there and all strings are having different linear mass density. The strings are fixed at both ends, and when the length changes, the frequency changes. That is well clear from the expression for frequency. So while playing chords, the guitarist will change the position of the finger. When the position of the finger is changed, the same string will produce different frequency sound, because change in length will change the frequency. When M changes, the frequency also changes. The first string is thick, therefore it will produce a sound which is different from the sound produced by the last string, which is thin. Change in tension will also change the frequency. So we can state the 3 laws of transverse vibration of a stretched string: frequency proportional to 1 by L, frequency proportional to root T, and frequency proportional to 1 by root M.